Now, the next topic I'd like to cover is the matrix determinant, and this is section 3.6 of Wessel's notes. Now, determinant is written in various ways, and one way is just to write Det of a matrix A. Another way is to put A between two vertical bars, and that means a determinant. And I want to make sure it's clear that this does not mean this is the absolute value of A. When you see a matrix between vertical bars, that denotes matrix determinant. And last, another way that I've seen a determinant described is with two vertical bars. So let's look at how to take a determinant of a 2 by 2 matrix. So we'll write our matrix as in terms of each of its components with the little a's, and we're taking a determinant, which again is denoted by the vertical bars. And for a 2 by 2 matrix, it's relatively simple. We just take the product of the first diagonal, the main diagonal of the matrix, and we subtract the product of the secondary diagonal. Okay, so the product of the first diagonal with minus the product of the second diagonal. Okay, for a 3 by 3 matrix, it's slightly more involved. And the determinant, I'm going to write it out mathematically first. And we're going to use the first row here to take our determinant. So it's going to be a function of each term of the first row. So the first term is, of course, A11 times M11. And I'll tell you what M is after I finish writing this out. And M, for example, M1J is the determinant of the N1 by, the N minus 1 by N minus 1 submatrix when the first row in the jth column is removed. In our case here, N minus 1 is 2. So in this case, it's a 2 by 2 submatrix. With, again, row 1 and column J removed. So if we write that out, we have A11, and if we remove the first column and first row, we're left with this lower submatrix, and we're taking the determinant of that. A22, A23, A32, A33. And I hope you can see that that's the submatrix with the first row and first column removed. So this is M11. Okay, and then we subtract the product of A12 times the determinant of the same submatrix when the first row and the second column is removed. So in that case, we're left with these terms, and that submatrix is A21, A23, A31, A33. And then the last term is A13 times M13. So we look at the first row, we remove the first row and third column, and we're left with this submatrix. And we're taking the determinant of that. And that is A21, A22, A31, A32. So we already know how to take a determinant of each of these 2 by 2 matrices. So writing that equation out, we have the determinant is equal to A11 times the determinant of the lower right submatrix minus A12 times the determinant of the second matrix with the first row and the second column removed. So that's the determinant of a 3 by 3 matrix. Now, the determinant of an n by n matrix, so a general matrix that has n rows and n columns, well, we could write that as the determinant of A is equal to the sum for j equals 1 to n of minus 1 raised to the I plus j power of the ith row of the element in the ith row and jth column times the determinant of the ijth submatrix. So here, I is any number from 1 to n, and that describes the row of the element we're operating on. And in the example of the 3 by 3 matrix that I gave, we used I is equal to 1. But the determinant can be used with I with any row, okay, being used for these coefficients. And the determinant's the same, whichever you choose for I, whichever number you choose for I. The other thing I wanted to make note of was that the determinant is only defined for a square matrix. Okay, so let's look at some examples. And I'm going to ask you to carry these out on your own by stopping the video. So the first matrix is that we're going to take the determinant of is a 2 by 2 matrix, and we'll just say that's 2, 1, minus 1, 3. And the second example is a 3 by 3 matrix. Okay, so these are the two matrices I'd like you to take the determinant of, and go ahead and stop the video and work through this on your own, and restart the video when you're done. Okay, so working through this, the determinant of a 2 by 2 matrix is just 2 times 3, which is 6, minus the product of the other diagonal, which is minus 1, and so the answer is 7. In the second case, we have to multiply 3 times the determinant of this lower right submatrix, and that's positive 3 minus 3, and that's equal to 0, minus 1, this top, the second column of the first row, times the determinant of the matrix when we remove the first row and second column, so that's minus 6 minus 1, which is minus 7. And then finally we have to add minus 1 times the determinant of the submatrix when the first row third column is removed, and that's 6 minus minus 1, which is 7. And when we do that, we get 0. Okay, so one interesting aspect of this last case is we got a 0 determinant. And one thing you'll notice about this matrix is that if you look at the second column and the third column, you'll notice that the second column is minus 1 times the first column. That is, if we can describe the second column as a vector. So for each element I of the second column, we write A sub I2, vector A sub I2, so it's the second column. Sorry to repeat that multiple times, but hopefully that's now clear. And again, the second column was equal to minus 1 times the third column. In other words, the two columns were linearly dependent. And I'll write linearly dependent as LD for short. So in general, when a matrix has linearly dependent columns, it satisfies the following equation where C1 times the first column plus C2 times the second column plus C3 times the third column equals 0. So this is a case where general case of linearly dependent columns. That defines the linear dependence of the columns. Now the rank of a matrix equals the number of linearly independent columns or number of linearly independent rows. Okay, in our case here, the rank of A was equal to 2 because we only had 2 linearly independent columns. The third column was -1 times the second. So again, our rank was 2. Now, if the rank of our matrix is less than its dimension, less than n, or in other words, 2 or more columns are linearly dependent, then the determinant is 0. As you recall, the determinant of our last matrix, which had a rank less than n, the rank was 2 and n was 3, right? That had a 0 determinant. And a matrix like this is called a singular matrix. So I'm just defining some terminology here. I should also note that any row or column of all zeros is linearly dependent on the other rows or columns. And this is also any matrix with all zeros in the rows or columns is also singular. And we've defined a singular matrix. A non-singular matrix has a rank equal to its dimension, and all rows and columns are linearly independent. And the determinant of that matrix is non-zero. Okay, so that does it for this video on determinant.